Good evening, and thank you, Wilf Earth Democracy, for this important program and the opportunity to participate in it. I am Pat Hynes, a retired professor of environmental health from Boston University. I also worked for the U.S. Environmental Protection Agency in their new hazardous waste program in the early 1980s as an environmental engineer. And subsequently, I worked as Chief of Environmental Management at the Massachusetts Port Authority, which includes Logan Airport. PFAS chemicals, until recently, were unknown to most, if not all, especially those in my work, environmental work, the best kept toxic secret by government and industry, given its widespread use since the 1950s and known toxicity to insiders, at least since the 1970s, if not before then. I will speak today about the new destruction technologies for PFAS, the family of chemicals notoriously difficult to break down into non-toxic components. Research at Duke University and the Battelle Corporation has shown that a process of supercritical water oxidation results in almost complete destruction of PFAS in aqueous waste, leaving only non-toxic byproducts. The US EPA is conducting promising research on destruction of PFAS in solid waste using mechanico-chemical degradation with non-toxic byproducts. Why is this needed? Current disposal technologies, incineration and disposal in landfills, do not destroy PFAS. Rather, they spread the toxic PFAS chemicals more widely into the environment, contaminating surface water, air, soil, plants, and animals, including humans. This graphic portrays the now familiar sources of PFAS, contamination in the environment, and ultimately the bodies of human and non-human animals. Consumer products, including paints and pesticides, fast food packaging, non-stick cookware, cosmetics, manufacturing parts, as well as firefighting foam. Researchers at Notre Dame University have found evidence recently that 1/2 of facial skin cosmetics contain PFAS, and they are the highest in waterproof mascara and long-lasting lipstick. And the FDA admits, quote, there have been few studies of the presence of toxic chemicals in cosmetics. I include this slide to make the point that in addition to civilian firefighting and firefighting training and exercises, the US military has been a major user of PFAS for fire suppressing foam, especially for petroleum-based fires in the US and throughout the world on its more than 800 military bases. As of March 2020, it's estimated that the drinking water of more than 700 US military bases and surrounding communities could be contaminated with PFAS firefighting foam. Many of the most contaminated drinking water sources in our country are on or near military installations, according to the Environmental Working Group. PFAS foam, as we see here, either from an exercise or a spill, will end up in local ground and surface waters, and from there, who knows, drinking water, rivers, and fish. Since the 1970s, the Department of Defense knew that PFAS is toxic in fish through the Air Force and Navy studies. Ignoring the research results, they have resisted taking their firefighting foam out of circulation. Under pressure, DoD will phase out current firefighting foams by 2024 and intends to replace them with short-chain PFAS. But evidence suggests that the next generation of short-chain PFAS chemicals may be just as toxic. This graphic shows all the sources of PFAS contamination in the environment. First, look at the lower right side of this graphic. Sewers carry most human, commercial, and industrial liquid waste to wastewater treatment plants. Thus, PFAS chemicals would end up present in wastewater treatment plants. The sludge they produce, which then may be put on farmland and grazing fields, and the effluent they discharge into rivers, bays, lakes, or groundwater. Next, look at the upper left side of the graphic. Landfills also leach liquid waste from PFAS-laden products such as carpets, clothing, Teflon cookware, cosmetics, into groundwater and nearby rivers. As the remaining parts of this graphic indicate, PFAS chemicals have been discharged from over 2,500 industrial sites around the country into air and waste streams. Airports and military bases have been a continuous source of PFAS used in firefighting foams and, consequently, contamination of ground and surface water. Thus, PFAS chemicals circle through the web of life into water, soil, plants, insects, fish, wildlife, and humans continuously. And because they do not degrade, they bioconcentrate in each part of the web. We excrete some through urine and feces, but slowly, and thus it builds up in our bodies. PFAS is found in the blood of most Americans and bioconcentrated in fish, seals, and polar bears. No place on Earth is untouched by it. A recent study of 50 breast milk samples from across socioeconomic and geographic groupings found PFAS contamination present in all of the samples tested, and in some cases at levels nearly 2,000 times higher than the 1 part per trillion level some public health advocates advise is safe. Also, the breast milk samples contained older and newer generation PFAS. Despite industry claims that, quote, newer generation of PFAS does not accumulate in humans, end quote, the study's authors recommend a complete ban on the entire chemical class. And what of the toxicology of PFAS? PFOA and PFAS, the two most common and most studied chemicals of the PFAS group, are linked to liver damage, reproductive and developmental toxicity, immune system harm, increased risk of thyroid disease, and increased risk of many cancers. The potential synergistic effects of multiple PFAS chemical exposures are not yet known. PFAS can be removed from water and aqueous waste by granular activated carbon filtration, and also by reverse osmosis, which leaves concentrated filters contaminated with PFAS from the home and commercial buildings or from drinking water and wastewater treatment plants. Then the question becomes what to do with the PFAS contaminated filters. The industrial incineration of PFAS contaminated filters and other waste is not hot enough to destroy them and thus contaminates local air and ends up in rainwater. Based on tests and new research that found PFAS widespread in rainwater, PFAS is likely detectable in all major drinking and industrial water supplies in the US, especially those that use surface water. So what are these chemicals that are collectively called PFAS? They are a class of an estimated 9,000 related compounds formulated with carbon-fluorine bonds. The carbon-fluorine bond is one of the strongest single chemical bonds, giving the molecules their persistence in the environment and their forever chemical moniker. The most commonly used and studied, as mentioned earlier, are PFOA and PFAS. The Battelle Company has developed a process using supercritical water oxidation This is a process whereby water, such as drinking water, or an aqueous waste, such as landfill leachate or wastewater treatment liquid, is heated above 374 degrees centigrade with pressure applied above 3,200 pounds per square inch, or PSI. This is the supercritical point of water. When oxygen is added to a supercritical liquid, a rapid breakdown of the PFAS in contaminated water, leachate, or wastewater takes place through oxidation. Battelle annihilator, which is what they call it, technology has achieved destruction to less than 5 parts per trillion PFAS, with minimal residence time, 2 to 10 seconds needed for this breakdown, and with no harmful byproducts. CO2, carbon dioxide, H2O, water, and naturally occurring fluoride minerals. This technology is currently being scaled up for field testing in early 2021. Other companies are also working with this process. Work at Duke University has achieved similar results to that of the Battelle Corporation. Using supercritical water oxidation, 110,000 parts per trillion of PFAS in the feed were reduced to 1 part per trillion in the effluent. Many other PFAS chemicals were reduced to below their detection limits. One of the disadvantages of this technology, the supercritical water oxidation, is that a significant amount of energy is needed to bring the waste stream being treated to the supercritical point of water. A lot of energy, however, can be efficiently recovered by heat exchangers. Another challenge is that the waste streams that is going in for this treatment can contain excessive grit or abrasive materials, causing plugging and corrosion in the equipment. Further, soils cannot be processed using this supercritical water oxidation. Today, after many years of development, commercial deployment of this destructive technology is on the horizon. So could a PFAS treatment unit become a part of a water treatment unit? Look at the top line of this graphic and imagine a PFAS treatment unit added after the disinfection unit. And imagine another PFAS unit added in the vertical line before the sludge digester. Both PFAS treatment units would destroy those chemicals, the PFAS chemicals, leaving the treated drinking water and sludge virtually free of the forever chemicals. EPA's research effort on destruction of PFAS began in spring 2020. Ball milling has been identified as a promising technology to remediate PFAS solid or semi-solid waste, such as sludge from wastewater treatment plants, and also contaminated soil. Silica, which is the major ingredient of sand, is added to the PFAS waste and placed in a rotating vessel with stainless steel balls. High-speed rotating causes high-speed collision of the balls with the PFAS contaminated sludge and silica, and consequently causes chemical reactions among the PFAS contaminated materials and silica. The end result is graphite, which is a carbon-based mineral, carbon dioxide, CO2, and fluoride minerals, naturally occurring fluoride minerals, all non-toxic. My final thoughts on the issue of PFAS destruction technologies is that this technology research is going to take off, given the sudden widespread public knowledge of PFAS omnipresence, given its toxicity and resistance to breakdown, and given increasing state testing and regulation, plus new federal legislative efforts. I recommend the Environmental Working Group's comprehensive website, and also searching the internet, as I did for this presentation, for the PFAS science and more accessibly written articles, as well as information about the pilot projects being conducted. My main sources for this presentation are on the final slide. Thank you for the opportunity of this forum.